continuing with completing the square and its methods. If we look at this situation here, we have another quadratic, but we have a problem. Up until now we haven't had any complicated coefficients in front of our x squareds. We've just had x squared, so 1x squared. Here we have 2 though, and that would mess up our method. So what we have to do if we have a coefficient in front of our x squared is take it out. Even if it makes the rest of the sum more complicated or adds in fractions, we have to take out that factor in front of the x squared. So we're going to start by doing that. So we take out that factor, minus 4x minus 1, and now the bit in the bracket is what we're going to form into our completing the square method. So now we have just the x squared. We go back to our x term and we say we need to break that into 2 equal parts, and that squared should be the number on the end. So if we take that, we're going to have minus 4. We want to break that into 2 equal parts, so that would be minus 4 all over 2. Well, that would be minus 2. And that squared ought to be the number on the end. So we're going to need to, it's not the number on the end, so we are going to need to add and subtract that on in order to create our perfect square. So we're going to have 2 on x squared minus 4x, and we're going to have to add and subtract. We must add and subtract so that overall we are adding 0. We are always taking the added on piece here because when we are forming our perfect square, you always end up with a positive number on here. And when we do that, minus 1, and all of that's inside of our bracket multiplied by 2, we've now created our perfect square. So this is in the form of our perfect square, so now we're able to factorize this. If we just factorize this normally, there's no special step going on here. If you factorize this normally, you will end up with the perfect square, x minus 2 to be squared. So we can do this out the long way as well, but as we know we've deliberately created a perfect square, you can just write it out this way. But if you factorize what I have underlined here, you will end up with x minus 2 to be squared. That's why we have constructed it this way. Then minus 4 minus 1 even, and we end up with 2 on x minus 2 to be squared minus 5, and we can multiply out our bracket, and y should be equal to 2 on x minus 2 to be squared. You're just multiplying 2 by each thing inside the bracket, minus 10. So this function would have its minimum, its lowest value, at x is 2, when this part is going to be 0, and then y would be 10. So when x is 2, you'd have y is equal to 2 times 0 squared minus 10. So you would end up with x with y is equal to minus 10, x is equal to 2 being the minimum, the lowest value for y that you would be able to produce from this quadratic. So that allows us to understand better what's going on with the quadratic. Now we can look at this function here, and I've written it in function notation, but it doesn't make any difference. This is still the y output of the function. And we need to take out our common factor, or not our common factor, we need to take out the factor in front of the x squared, whether it's a common factor or not. We can see here that that's going to make a messy fraction of our coefficient on the end, but it doesn't make any difference, of our number on the end I should say. We still have to take out that common factor. So minus 5 on x squared minus 6x plus 30 all over 2. If we have changes of sign going on, we need to be quite careful. We took out the negative factor because we need 1x squared here, so we need to be quite careful that all of these signs are going to change, because if we multiplied this back out again, we would need to end up with our original situation. So now that we have done that, we can start forming our this part as being our perfect square as normal. So we can have our minus 6. We know we would want to break that into 2 equal parts if it was a perfect square. So we half that coefficient, and that would end up being minus 3. And we should have minus 3 squared on the end if we had a perfect square. Now we don't, So we're going to have to create that situation. We're going to have to add and subtract on minus 3 to be squared in order to form a perfect square for part of our function. We have x squared minus 6x plus minus 3 to be squared. Always adding on the squared part is going to be the perfect squared part, minus the bit that we have to minus it, so that overall we're adding 0, and we have our messy fraction on the end. It hasn't gone anywhere, and all of that is in the bracket multiplied by minus 5. So now we have deliberately formed this into a perfect square, and again, if you factorize this normally, you will just end up with x minus 3 to be squared. So we can say minus 5 on x minus 3 to be squared, and then we'd have minus 9 plus 32 all over 5. Now at this point I could start doing this as fractions, but I can see if I multiply this out I end up sorting that I don't have to tidy up fractions. So I'm actually just going to multiply out this bracket now. So multiply minus 5 by each thing inside the bracket. So I end up with minus 5 on minus 5 even on x minus 3 to be squared, plus, remember we're multiplying by a minus number, and now we tidy that up, so we end up with y is equal to minus 5 on x minus 3 to be squared, plus 13. Now, this is a little bit different. This is actually the function f of x graphed. And what we can see is this is a negative quadratic. So a negative quadratic would be a frowny face, negative, a frown. So as opposed to the smiley face, the positive quadratics that we had before, we now have a negative or a frowny quadratic. So what consequence does that have for completing the square? Well, we know that the part of this that is squared has to be greater than or equal to 0 for any value of x. But this is now multiplied by minus 5. So overall, all of this bit that I have underlined has to be less than or equal to 0. It has to be less than or equal to 0. Because this bit, the bit that changes, is always greater than or equal to 0, and it's multiplied by a negative number. It's multiplied by minus 5. So this part is always going to be a negative number or 0. So now the argument is the same, but it has a different consequence because of this negativity. When x is 3, so if we found where this part is going to be 0, that'd be when x minus 3 is equal to 0. So when x is equal to 3, the changing part would be 0. So we'd have y is equal to 0 squared plus 13. So you'd end up with y is equal to 13 would be our highest value of y that we could get. We say the maximum value of y. Because for any other value of x that we put in, say again if x was equal to 1, we would have, I'll write it out, when we tidy that up, we end up with y is equal to minus 7 when x is equal to 1. Now I just picked x is equal to 1 as a random example. There's no significance to the particular number I picked. Any value of x that isn't 3 is going to result in something being taken away from this plus 13. When x is 1, we end up taking away 20 from 13 and ending up at minus 7, which is way off the graph that I have drawn down here, but you can see it's going negative very quickly. What matters is we recognize that for any value of x other than 3, you end up subtracting something from 13. So you end up with a lower value for y, which is why when we look at our graph, when x is 3, we're at the top of the hill, and we have y is going to be 13. Because for any other value of x, you're subtracting something away from that value of 13. Now, we can use this tool of factorizing, I should say, completing the square, to solve quadratics as well. So we're going to look at that as our final piece of work. So if we have the same quadratic and we are asked to solve when it is equal to 10, well, we could rearrange this to get it, subtract 10 from both sides and factorize it, or use the minus b formula. That would be perfectly fine. But we can also use completing the square, and we're going to look at the significance of doing that in this example. So we're going to complete the square of our original quadratic, just like we did here, and we know that we end up with f of x is equal to minus 5 on, is just what we got here, minus 5 on x minus 3 to be squared plus 13 is equal to 10. So now what I'm going to do, now that I've completed the square from what I did in the previous part, I'm going to rearrange this to find my values of x. So you just rearrange this equation as you normally would. So get x by itself, minus 13 from both sides. We have minus 5 on x minus 3 to be squared is equal to minus 3. Divide both sides by minus 5. The only unusual thing about this is our variable that we are trying to isolate is a little bit more hidden than it normally is. It's in the middle of this squared bracket. But we know what we do. We just isolate our terms. And now what we have to do is take the square root of both sides to get that bracket out from underneath that square. If we take a square root, we have to consider the possibility that it was either positive or negative to begin with. Because when we'd square minus 3 over 5 or plus 3 over 5, you would, or square the square root of this, you would end up with plus 3 over 5 in either case. So anytime you take a square root, you always have to take into account that you could have the positive or negative solution. So that's now gotten rid of our square on our bracket, and now just add 3 to both, add 3 to both sides. And we end up with x is equal to 3 plus or minus root 3 over 5. Now this looks very like the solutions that we get from the algebra formula, the minus b formula. And that is because the minus b formula actually comes from completing the square. That is the origin of that formula, and you can show that in general. But for right now, we just want to have a look at the function and make sure that we're happy that we have actually gotten solutions that we want. So if I put this into my calculator to get easier to read numbers for x, when x is plus 3 over 5, and when x is 3 minus root 3 over 5, I get x is equal to 2.23, and I get x is equal to 3.77. When I look at my graph, does that actually work out? Well, I'm looking for when y is 10, when my function output is 10. So I go across there and down, I get about 2.2, that's not bad. When I go across and hit it again, I get about 3 3/4. So that looks correct in terms of the values that I got. Again, this is true in general. The minus b formula, minus b plus or minus the square root of b squared minus 4ac all over 2a, that formula comes from completing the square. And we can use completing the square to solve the same problems as we might use with the minus b formula. And that is what we need for now.